Good afternoon. So welcome again to the lecture course on quantum gravity. Today we arrive at chapter 6, which is devoted to loop quantum gravity. Now, so far, if you remember, we have discussed the canonical quantization of general relativity in the metric variables, in the geometric variables, leading to the Wheeler-DeWitt equation, the momentum constraint, which are timeless equations. We have also shown how time emerges in the semi-classical approximation as an approximate variable. Now, loop quantum gravity is a different approach of quantizing general relativity. So again, general relativity is a starting point. You quantize, and it's also a canonical approach. So it's very similar to what we have done before in chapters 4 and 5 in geometrodynamics. The main difference is that different variables are used. So we will not use, as you will see, the metric or the three-dimensional metric and the second fundamental form. We will use variables that are defined through a canonical transformation from them, but which have more the interpretation of variables you know from Young-Mills series, like quantum chromodynamics with vector fields and color electric field. So in this sense, conceptually, I would say it's very close in the spirit, say compared to string theory or others, but the details are different. Now, of course, this is just one lecture, so I cannot do full justice to all the details, but I will try to present the essentials. So if you want to have the details in my book, of course, you can find many more details and also references to other literature. There are also some books by the pioneers of this approach where you can find many, also calculational details. I divide this chapter up into, as before, the classical part and a quantum part, because we need, unfortunately, many classical preparations before we really discuss the quantum theory. So this is section A, which is the classical part. And what we will aim at is that instead of this canonical pair of geometrodynamic variables, so the three-dimensional metric and the geometrodynamic momenta, which are linearly related to the second fundamental form, in how a surface is embedded into the fourth dimension, by a canonical transformation. So canonical transformation is a transformation that mixes P's and Q's but preserves Poisson brackets. No? So this here corresponds, generally speaking, to the Q's in the mechanical language, and this to the P's. And we have new ones, and you will learn about them, A, I, E, B, J, so they will be defined below. But so this will be defined from the three metric, but it will play the role of momenta. So somehow the role is also switched between the two. So this would be the P, and this would be the Q. There's these two variables are sometimes called Ashtekars, new variables, because Abhay Ashtekar in 1986 introduced these variables as an alternative to canonical geometrodynamics. So this here are sometimes called. Now, of course, it's by far no longer new, but this is how it's often labeled, new variables. So this is from 1986. No? So Wheeler-DeWitt, and this is from the 1960s, and so this has started in the 1980s. And one of the main motivation is this analogy to Young-Mills theory. Now there are two steps, and the first step of this is independent of Ashtekar 1986. This is some standard formalism that partly was presented by me in the relativity course, that you instead of metric have these tetrads, and the formalism. Now, of course, because it's three-dimensional everything, it will be triads or Dreibeine, as one also says in English, Dreibeine instead of Vierbeine or tetrads. No, so the first step is the introduction of triads or Dreibeine, and they will play the role of the momenta. They will be related to this capital E later, but first they are small e's, and we call them EAI of x, and so this is an orthonormal basis, also normal basis, O and B for short, at every space point. No, we are in three-dimensional space, as in the old canonical formalism, not in four, in 3 dimensions. This is why I call it triads. And they have two different indices. The A, which is the upper index, stands for the space index, not like it's a vector index, and the I just labels them, it just counts them. For example, you have here, if they are orthonormal, just this picture, you can write it E3, E2, and E1. So this is in the tangential space, and then of course it's flat, then you can just form the usual Dreibein, the orthonormal vectors. So this index I is the 1, 2, 3, and its position is arbitrary. This is just convenience, whereas this is here the usual space index that is transported by the metric. So A is 1, 2, 3. So this is the space index. So at in the tangential space at point X, which is in the three-dimensional space, there's a tangential space, a three-dimensional tangential space where you have this. And I is also 1, 2, 3, and this is an intrinsic index, just counting the vectors, counting the basis vectors. Okay, we have an orthonormal system. This means that if we take the three-dimensional metric, the scalar product is the Kronecker. So you have here this HAB EAI EBJ is a delta IJ. So this is orthonormality, and from this you can also get the relation for the inverse metric. So HAB is delta IG EAI EBJ, or we can also write this as EAI EBI, because the delta, you can put the indices, the intrinsic indexes, wherever you like. So in a sense, you could call this Dreibein the square root of the metric, metaphorically. You see, this freedom, as we did in relativity 2, there was a tetrad, it was in space-time, but it introduces a new symmetry, a rotation symmetry, because you can, have this basis, but you can, of course, rotate it, and you do not get any difference in the mathematics. So this brings into play an SO3 symmetry, which is the rotation symmetry. So new SO3 symmetry. Respectively, if you're on the quantum theory, you may also try to use an SU2 symmetry. I just write it here, but classically you would just have a rotation symmetry because of the invariance of the metric under local rotations of the triad. Now, connected with this triad are, of course, the, in a sense, co-triads in the cotangential space, as we had also in the four-dimensional case in relativity. So connected with AIE, we have the A, I call it AIA of X, just having this index. Well, this position of this does not matter, but this space index is putting down, as we have used also for forms, not general warm forms. ARX. So this is an also normal basis in the tangential space, which I think we called Tx star of sigma, so the three-dimensional space, and at point x, and the cotangential space, so which give you the linear transformations from the vectors into the real numbers. So this is a basis of one form, and we have that they are in the following sense inverse. EIA times EAJ is delta IJ, and EIA EBI is delta BA. Yeah, okay, this is in a sense old stuff, just reviewed. But what is new now and what is important for Ashtekars variables is this capital E. And this capital E is a densitized version of this small e. Densitized means you multiply it by the square root of the determinant of the 3 metric. And then you get a density. A density is something that wants to be integrated over. So we have this EAI, so that's what enters here, of x is defined as the square root of 8 EAI of x. No, so recall this is h is a determinant of the 3 metric, we had it before, and one can show that this is identical to the determinant of these matrices EIA. Just leave this as a short exercise. It follows actually if you'd have this equation and you perform the determinant on the left and the right hand side. And so the determinant of this here is then just h, no? Because you have here this is 3 times 3 matrices, so the cube of this, and this is then 1 over square root of h. Okay, now we have the capital E, but for the canonical formalism we need a canonical momentum, a p. So what is the p? We know from here that conjugate to that is something that has to do with the second fundamental form. And of course this should be preserved, yeah, but we will have second fundamental form then transformed a bit. So so the canonically conjugate quantity so let's define the following new variable KIA, so which has also like the E these mixed indices, intrinsic and space index at a point x, and it's defined by the standard form of the KAB, the extrinsic curvature at point x, but multiplied and summed over here is this index by EBI, by the triad. No? So that's the extrinsic curvature, or the components of the extrinsic curvature. Now this is already conjugate to this here, up to some factors that we have redefined in the following way. So I leave this as a short exercise. It's in the book explicit. You can read it, of course, but you can also try in 3 lines or 4 to check this. So we have, what we find is that KIAI DEIA is, after this couple of steps, is minus 8 pi gravitational constant times PAB times DHB. No? So if you make an infinitesimal transformation, or variation, I should say, of E and multiply with key, you can show this relation, that apart from this factor, it's the same as here in the original PDH. No? So they are canonically conjugate variables, up to this factor, of course, which you can take into account. Now, we have, in addition to what we had before, this freedom of having this rotation. And one can show that the SO3 rotation of the triads, they are generated now by a new constraint that comes in addition to the old constraints that we had before. And this constraint is called Gauss constraint. So the SO3 rotations of the triads are generated by, and I write it down, so I call it a curl G. It has an index I, so this intrinsic index at each space point, and it's the epsilon symbol, the usual epsilon symbol, times kja of x, no, this is the k here, and times e ka of x, and it's 0 as a constraint, so we wrote that in this Dirac way, so this is 0 as a constraint, and it's called the Gauss constraint. Yeah, so why this has to do with the rotation, so it looks a little bit like what you know from mechanics, R cross product P, no, which generates rotations in three-dimensional space. So this E plays the role of the momenta, and this K will have then to do with the conjugate quantity or with the configuration variable. Of course, one can show this explicitly in that one. Maybe I have it later. Calculate a Poisson bracket of this with quantities and see then that it generates rotations. So this is a generator of rotations. Okay, and also one can show that their present guarantees the symmetry of this here. Of course, we know already before that this is symmetric, but one can show that this is consistent with that, and that KAB is KBA on the hypersurface defined by this equation. Okay, now we can again, in the spirit of what we did in relativity 2, we can expand any vector field into these triads. In the relativity 2, these were the tetrads, here are the triads. So expand vector fields into triads. Then we write it in the form VA. As in relativity, I mean, we had this notation was so-called abstract vector notation, so that this does not necessarily stand for the component, but that component stands for the whole vector, no, as is usual in relativity. VA, and we can expand this as VI, EAI. No? So that's then the first component times this vector plus the second component times this vector times the third component times this vector, as we usually do. Then we can have also a covariant derivative with respect to the intrinsic indices, with respect to intrinsic indices, and I call it DAVI, and it's defined by, as usual, first the ordinary partial differentiation plus then omega A I J V J. Now what is this small omega? If you remember relativity 2, we had that too, this and called it a so-called spin connection. Yeah, it's a generalization of the Christoffel symbol. It will be connected to the Christoffel symbols, as you will see, but it's more general, and it has these intrinsic indices that refer to a general basis. We also called it an unholonomic basis, not necessarily derivable from coordinates. So that here is the spin connection. Spin because this is also the quantity that is used if you couple two fermions. because there you have to use this formalism, and the metric formalism is not sufficient. This is where this name comes from. No, so in usual relativity with coordinates, we had not in this formalism. You know that we had this relation, and then we had just the gamma, the Christoffel symbols. You know, so that certainly you should remember, and we with the anholomic basis we had this generalized formula. Yeah, so this omega, this spin connection, omega a ij, we can, and this is what we had, we can, because this here it has one downstairs index, so it can be considered as a one form, and these are additional indices, so it's an ij valued one form, and the expansion is ikj eka. No? So this, you have this different type of indices. So here this index is then here the one of the form, and the other they just accompany it. And this gamma is already very close to our Christoffel symbols. One finds explicitly for this the expression in gamma I kj is, I just write it down, I say some words on it, e dk e f j e I c, and we have gamma c df minus e dk e f j and the partial derivative of EIF. Now, so you have typically for this gamma, so this inhomogeneous term, so this here is the usual Christoffel symbol. Usual Christoffel symbols. And this is this inhomogeneous terms which has this derivative of the EIF. And for the, we have here defined the covariant derivative. If you apply it to the triads themselves by the usual rule, then you have the A EIB minus gamma CAB EIC. Not minus because it's downstairs, and this is the usual space part, and then here comes the intrinsic part with the omegas A, I, J, E, J, B. No. And this you can expand as, you put this here in, and then I leave it also as a short exercise. Once you put this in and manipulate, this turns out to be 0. So the triad is covariantly constant. And this is also called metricity, and this corresponds to the covariant constancies of the 3 metric. In space-time, it was the covariant constancy of the 4-dimensional metric. G mu nu semicolon nu is 0, and that's the version in 3 dimensions, and it also holds for the triad, for this for this covariant derivative. So that's important. There are more general theories of gravity, so-called with non-metricity, where this is violated, but here it is satisfied. So here, and this is to be observed in all calculations. Now the connection, as you know, has to do with parallel transport. This is where the name connection comes from. It connects neighboring point by parallel transforming vectors. In flat space with Cartesian coordinates, it just stays the same, the parallel transport, but otherwise it can transform. So we have a parallel transport. Of a vector, so with here just the intrinsic index minus omega a I j bj dx a, and we define another version. So here I mean, old friends come always into play, but there are also versions with different type of indices, like here the IA, and there will also be a gamma with IA, also a Riemann tensor with different components, and this is minus 1/2 omega a j k epsilon I j k. So then you get that. Why? Because I mean this occurs in an easier and simpler way in formula. No? So we have then from this we can d omega a rotation, infinital rotation by just gamma ka dxa. I mean, okay, dvi is epsilon I jk vj d omega k. So that's what the parallel transport does, no? And so this here is then the change in this omega k. So it's an infinitesimal rotation, of the vector vi by an angle d omega k. Okay, so far so good. That's more or less old stuff. It has nothing to do with canonical gravity so far, nothing to do with Ashtekar's new variables. It's just a reformulation, a geometric reformulation. We do not even have discussed Einstein equations. Just a reformulation of differential geometry instead of metric, using these triads or tetrads in 4 dimensions. No? And yeah, I gave a longer discussion in Relativity 2 about the need. I mean, here in that lecture course, we only needed today for the loop quantum gravity. So for the remaining lectures, we will go back to geometrodynamics and will not use it. But it's nevertheless, even if you are not interested in loop quantum gravity, it's nevertheless important to know this formalism. For example, if you couple fermions. Also in traditional geometrodynamics, you have to switch to this if you discuss fermions and spin 1/2 in particular. Yeah. Okay. So that's the first step. Now, well, okay, maybe a brief remark about the number of degrees of freedom. Okay, A and I independently go from 1 to 3. So these are all in all 9 variables, the EAI, no? All in all 9, analogously to this here, 3 times 3. But the 3 metric only has 6 variables, and we should have the same independent degrees of freedom. Now, how come? The answer lies in this constraint, because by having these new variables, we have got a new constraint to deal with because of the freedom to make rotation. These are 3 equations. So we have 3 times 3 minus 3, and again come to 6 variables. Okay, so this is the first step. I should use that here. Now comes the second step, which is really what Ashtekar did in 1986. So this is the second step. And this is, I should, okay, again, emphasize this. So what did he do? He defined now this capital A, this analogous quantity to a connection, to a vector potential. And it's defined as follows: G times A I of x. So that's the gravitational constant. Is defined as gamma IA of x plus, there's a parameter, a new parameter. I inserted here beta times KIA of x. I will say, of course, something on that. Okay, so that's then the second equation. The first was that here, and this is the second. Now I'm not totally correct historically because Ashtekar in 1986 had chosen a particular value for beta. He chose the imaginary unit. I will say something on that. But the modern formulation is to keep this open and have here a general parameter that can be complex, but not zero. Because if it was zero, then this k would be away, and then the a would just be the gamma, and this would not make any sense. And the name in the literature of this beta is Barbero Irmizi parameter. Now, after two independent papers by Spanish physicist Barbero and Italian physicist Irmizi. Now this left-hand side has a dimension length to the -1. No, like the right-hand side. And so if we multiply this by some length, it becomes dimensionless. No? So G A I A times dxa, this is then dimensionless, and this is what you can then what you will then integrate over loops later. This dimensionless quantity, this is what you integrate. So this is the loops later. No, so later we will not use the A itself, but the name loop quantum gravity comes from loop, I mean from Schleifen, and so you integrate this over one-dimensional loop, as you will see. We still have time. Yeah. Okay, so now we have Ashtekar's new variables, and one can then calculate the Poisson brackets between them, and because they come from a canonical transformation. And yeah, I mean, this canonical transformation was between the k and the e, but this gamma is only, I mean, depends on the small e, so one has to check that this does not disturb this transformation, and it turns out that this is 8 pi beta delta ij delta ba and the delta function. So it's equal to 1 in a sense, except for this factor you can of course redefine this, so to have the standard form delta on the right hand side if you like, but this is what usually is done. And aia of x and ajb of y is indeed 0. I mean, this is not clear if you just look at it. You have to calculate to see that, I mean, the q's among themselves have Poisson brackets 0, no? Like in mechanics, q1, q2, 0. Only q and p. So the idea here is that a is the new configuration variable. It's the new configuration variable. And the e is the new canonical momentum. And this choice comes, I mean, and not the opposite one, from this analogy to Young-Mills and even to electrodynamics. In electrodynamics you have a vector potential A, which is the Q in a sense, and the electric field is conjugate to A. Now A in electrodynamics is connected with the magnetic field. So in electrodynamics, electric and magnetic field are conjugate to each other. And the B is the Q and the E is the P, and this is why this is chosen. If you go to QCD or to the standard model of particles, then you have these non-abelian fields. So in electrodynamics there is no I, J, no, but in Young-Mills series you have this. But this property remains. Now, what have we to do? I mean, basically, in the rest of this lecture, we have to discuss the constraints. how they look like, and then to quantize and look maybe for solutions. We have already seen that we have this new constraint here, but of course we have to take care for our old friends, the Hamiltonian constraint and the diffeomorphism constraint, because they were central in canonical gravity and they have to be rewritten in this form. And Ashtika's hope originally was that this choice would simplify the constraints. You will see whether this hope has been fulfilled or not. But that was one further motivation. Two motivations for him. First, having something similar to Young-Mills, and then maybe being a step closer to unification with, say, standard model, where you have these variables. So if also gravity, you have these variables, and you would think, maybe you can have just one theory. And second, to simplify the constraints. You will see. Okay, we already had this constraint here, and we can rewrite it in terms of the new variables. Okay, the E is already there, but instead of the K, we can use the A. Okay, maybe so rewrite constraints. So the first is the GI, which was what is written down here, and one can show after some calculation that this is equal to that, plus gravitational constant times epsilon ijk a j a e k a, and that is a constraint, so I write Dirac equal to 0. Now this is again a covariant derivative, but it's a covariant derivative with respect to the intrinsic indices, so this is, you could write as a curl D A. So it's a new type of covariant derivative, not to be confused with this one, because it has to do with A. Now A is here the potential and not the gamma. Like in electrodynamics, where you have partial differentiation plus electric charge times AE. No? So this is the covariant derivative associated with AIA. Okay, you know from electrodynamics and maybe from Young-Mills, if you have learned about them, that, okay, you have this vector potential, but there's also a field strength associated with it. In electrodynamics, you have the A, and the electromagnetic field strength tensor is then dAAB minus dBAA. And this we can also define for non-abelian fields and also here. So we have a associated, okay, field strength, but we can call it in the geometric spirit a curvature, no? Because this is what you have in relativity. It's the curvature, the first derivative of the connection and the second derivative of the metric or the triad. These are the curvatures. You could also call it field strength, if you like, associated curvature. So, and okay, this has two indices concerning the space, but in our case it has one intrinsic index, and it's defined as 2G then dA AB. So that's the antisymmetric combination, dAAB minus dBAA, known from electrodynamics already, but we have here, because of this index, and this is also what you have for quarks and gluons and the like, we have a second term that is quadratic in the A, but no derivative. A, J, A, K, B. No? So that's similar to Young-Mills series. So similar to Young-Mills series. Okay, and so you can check then now with this Gauss constraint. I mean, I should emphasize that covariant derivative of E equals 0. Of course, this is very much like, this is where the name also comes from, the Gauss constraint in electrodynamics. For vacuum, the divergence of E is equal to 0. And you see how all these things repeat, they become more complex with more indices, but in principle it's the same mathematics and the same idea that is behind. This is why it's called Gauss constraint, because it has the form of the Gauss constraint in electrodynamics. You can calculate, the changes of E and A under action of this Gauss constraint, and you will see that these are just the gauge transformation, Eichtransformationen, gauge transformations of the Young-Mills field. And it's relatively easy shown, so integral dy, I should say d3y, but for short, to save writing, I write it in this form, but you know it's three-dimensional. And so psi I is just a parameter, and you get here minus 8 pi beta g epsilon I jk e ka psi I. And well, in electrodynamics, this turns out to be just 0. The electric field is gauge invariant, as you know, but the color electric field, say in QCD, is not gauge invariant. It transforms, and the A is the integral dy a of x g j of y. You get minus 8 pi beta, and you have dA psi A. Now, in electrodynamics, this is changes, and the A, when you make a gauge transformation, gets shifted by the gradient of a parameter, and here that's a generalization here of the gradient of the parameter. You have the covariant A derivative with respect acting on psi. Yeah, often it's also convenient, and people do that, and this is why I have to show you, even at the price of having another notation, that one can write just this with one index, and this is defined tau I EAI, and these taus, they are basically the Pauli matrices. So, that's a kind of standard machinery in Young-Mills theories. So here, this is I over 2 times sigma I, and these are the Pauli matrices. Now, so you have a matrix notation instead of index notation. Yeah, so that's is often convenient. You can use one or the other notation, or you can swap. For example, under SU2 transformations, small g, then you get these results. This is what you find in all the books on Young-Mills theory and the standard model, that this is just something like a rotation, the gauge transformation, and the AA goes like G AA plus DA times G minus 1. Now, so that's a connection, and this has another interpretation, and this is connection means that it's not linear here, this transformation. You have here this gradient term. You see this everywhere, also in the Christoffel symbols when they transform. Here now you have this D. So all the connections, when they transform, they get such a term, maybe with indices and the like, but no. And so that's important, and you see again one advantage of this formalism. You get results that you find in the particle physics books. Yeah, now we have these other constraints, and we have to spend some effort, or Ashtekar spent some effort in 1986 to rewrite these other constraints in terms of these new variables. So we had, the other constraints, and so these were the Hamiltonian constraint. G, this refers to the gravitational part. I don't go now to add matter fields for the time being, the constraint, and the momentum constraint. So we are still classical, so no Wheeler de Wit yet, so classical constraint. Remember, this is very central for Einstein's theory. This corresponds to the G00 Einstein equation, and this to the G0A Einstein equation. But they are constraints because they restrict the freedom of choice of initial data. You cannot choose initial data freely. This is why they are constraints. And the remaining 6 Einstein equations, they really evolve you. Okay, you have to rewrite them. So rewrite in terms of this couple I, A, E, U, J. This is more or less difficult, but it's a kind of straightforward, and I guess every one of you just taken enough time would be able to do that, and you can read it in my book or in Ashteka's paper. I just give you the results. So let me first discuss the momentum constraint, which is the easier one, HA. Actually, one defines it first in such a way that one adds here a factor minus HIB beta times the AAG. So you take the usual one. So for laziness, I don't write here a G as as standing for gravity. And the tilde means that, okay, I have this factor. And I also add something proportional to the Gauss constraint. So, of course, these constraints, they're all constraints, so they are 0. So on the constraint hypersurface, if I add another constraint, I don't leave the constraint hypersurface. So why is this done? Okay, Ashteka has done it to get as simple an expression as possible as a new constraint. And so the calculation then shows that this is F I A B E B I. So that's, so to speak, the redefined and rewritten momentum constraint. So that's a constraint in here. In fact, so this is the curvature here, what we just defined, and this is the A field. And again, this is linear in momentum. Recall the momentum constraint in geometric dynamics is also linear in momentum. And one can actually show, because of this here, that this generates diffeomorphisms plus gauge transformation. So if you apply this on a quantity, it transforms them, and the transformation is a 3-dimensional diffeomorphism and a gauge transformation. Now the more intricate one is certainly the Hamiltonian constraint, as always. So also this is a constraint that we redefine, and it's called H orthogonal tilde, which is again minus 8 pi g. Now it's a beta squared. Beta is this parameter. So in a sense, you have a whole family of new variables. For each beta, you have one. So you have, in a sense, more freedom. H orthogonal g, and then again a term, but it's a more lengthy term, and you will not be enlightened by seeing this term. So plus a term proportional to this constraint here again. And okay, the calculation gives then the following. Okay, it will depend, of course, on beta. Perhaps you remember in the usual Hamiltonian formalism, I mean the space-time metric we have written as, I mean, the signature as diagonal sigma 1 1 1. No? So this is the space which is positive definite, and here this is -1 for space-time. Or it's 1 for Euclidean, for four-dimensional Euclidean. And because in physics and also here, I mean, a Euclidean formalism is often also discussed and is important. This is why I again have this parameter sigma. No? So if you're only interested in space-time, then the sigma is always -1. But you can leave it open, and you get then the following. So you get two lengthy, or well, two terms, one looking a bit lengthy, minus sigma over 2, and you have here epsilon I j k f a b k, square root of the determinant of e a I, and then you have a quadratic term in the momenta, in the color electric field, E squared. So this would correspond to the kinetic term, the p squared, no? Like in mechanics, p squared over 2m, the kinetic term. But then there's also a potential. Well, I was not totally right, because this is mixed. We will later disentangle. So there will also be a quadratic term now, and you have here beta squared sigma -1 over beta squared square root of determinant of e a I, e a I, e b j. So, and this symmetrization, and then we have here g times a I a minus gamma I a, and we have g a j b minus gamma j b. Okay, it looks a little bit lengthy, but the Hamiltonian constraint does not make life easy for us usually. So that's here. And it's, of course, 0 as a constraint. No? But it's now rewritten. It's the old Hamiltonian constraint, just modified by these two and rewritten in terms of Ashtekar's variable. Now, here comes the role of sigma into play. So Ashtekar's original idea was, I mean, one of the two motivations to simplify it. And he said, aha, I can simplify this drastically if I choose beta appropriately. So Ashtekar in 1986, he then chose beta equal to I, or I think you can also have plus or minus I. I don't remember actually whether he has fixed the sign here. Because then you have here a -1, and for space-time, sigma is -1. So -1 times -1 is +1, -1 is 0. So this means this whole second long term, which is the more complicated term, vanishes. So potential term, okay, it's called potential term. Okay, potential term. So potential term vanishes for sigma equal to which is the physical case, no? Space-time. Of course, if you want to have an Euclidean formulation, then beta equals to +1 would be a good choice, because then this would be +1, and then you just choose beta squared is equal 1, so beta could be plus or -1. So beta is plus or -1, so then the potential term vanishes for sigma is +1, which is the Euclidean case. Euclidean case. So, if we go back to what Ashtiger had, so for beta here, here I have is plus I. So then we have, if we multiply also the constraint by a factor, say square root of determinant EAI H tilde orthogonal is then epsilon I JK F ABK EAI and EBJ. Yeah, constraint is here. So that looks much more sympathetic than the original one, because it's just here quadratic and this complicated potential term, and from the Wheeler-DeWitt equation or from the old form of the constraint, the potential term, you have this three-dimensional curvature, and this is what prevents the main obstacle to solving the Wheeler-DeWitt equation generally. So Ashtiger said, no, we can solve these problems by going to these variables, because then the potential term is away, and we can just use this, and in the quantum theory, which will be then discussed soon. However, things are not always that easy as you may think, because then here, in that case, the dA would become complex. Complex. So that's not what we want, because in relativity everything is real. We are not in quantum mechanical wave functions. So at that time the opinion was, that's clear, but we have at some point to impose reality conditions on the solutions. But it turned out, unfortunately, and so because we are in 2024, not in 1986, I can tell you that this failed. This imposing reality condition failed in the quantum theory. Before that, well, it was only then in the 1990s. Before that, in the quantum theory, which we'll discuss in a minute, exact solutions were found here. And so people and also maybe students working at that time, they were busy with finding exact solutions to this. You could classify, you have nice solutions classified in terms of knots, Knoten knots in the quantum theory. But after all, it was not, clear how to impose the reality condition. You could not just have real part of everything. So you would have, all what you got was, a quantum theory for in the Euclidean case, for a signature 1111. So the modern attitude is you just have to live with the beta. I'm probably having beta real, but in principle it can be complex, but the attitude is to have a real beta. So complex, so reality conditions, it's unclear. And so attitude is choose real, beta, and this is what Barbero then also, well, Barbero had this general beta then, and for example he had Barbero beta equal to -1. This was in 1995. If you have that, then of course this term comes into play. There is no way out. You have this term, and you have the following expression then for the constraint, which is let me write it in terms, because then it's less space to write on the blackboard with this gamma, with this tau matrices, with this Pauli matrices. So it's then 1 over square root of the determinant of the 3 metric. And that trace, or the trace, refers then to the 2 times 2 matrices, because I write it in this form. All of these quantities are 2 times 2 matrices. And trace is just a trace of these matrices. So, and then you have here FAB, now without the I, because FAB is FABI times the tau I minus 2. And we also have a curvature that you can define as a matrix. And then you just have a commutator in terms of matrices of the eBay. Okay, so that's how it is. Okay, it's now a short notation, but still you have again this here, like in the old version, the 3-dimensional curvature comes here again into play. So this simplicity that would have been here is not present. So in a sense, you're back to the old geometrodynamic version, and it's not easy, or at least as I would say as difficult or impossible to find exact solutions as in geometrodynamics. The algebra of the constraints basically remains unchanged. Recall we had the algebra between Hamiltonian constraints and momentum constraints, and it closed classically with the Poisson brackets. Now we have in addition this GI which comes into play, but also this all of them commute in the Poisson bracket sense. So the algebra of the constraints is unchanged. And I should say that, and I have no time, unfortunately, to discuss technical details, but there was an important rewriting of the Hamilton constraint at that time by Thiemann in 1996. So he had a rewriting of the Hamiltonian constraint in terms of a 3-volume and related geometric quantities. I mean, you find the details in the book and the original literature. I think it's not absolutely needed to write it really down. I can tell you what one does with it. It's just a new form of the same expression with the volume and others that one can use for getting an important result that I will present you at the end of today's lecture course. So, of course, now we have E, which is the densitized triad, and we have A, which is the gamma IA plus Barbero-Amici parameter times KIA. Instead, now we introduce the loop variables. So instead of AIA, EBJ, use things that are integrated over to some extent. Yeah, one reason is that in the quantum theory, because they are local on X, they are highly singular in a sense, and so one writes them as a so-called holonomy. This is something you integrate over a one-dimensional loop, and the flux. This is something that if you have a loop, you have a surface that is enclosed by the loop, and you have a flux of field lines that goes here. Yeah, here. So here you integrate over a two-dimensional thing, which is a flux. You know, flux from flux of magnetic field and electric field, and the holonomy is here. And the holonomy is something that you have something like the exponent, and then you integrate over gravitational constant times integral over a, and so this is the alpha. You must also introduce a so-called path ordering, which I will not discuss here, but basically that's it. So this holonomy. And the flux, yeah, you will see then it is the integral over, if you have this surface. Surface S, so then it's the integral basically over the surface with a, and you have the E AI, and of course you have some surface element sigma IA. This is just briefly, I will do it carefully later. No? So then you have here things that have a two-dimensional integration and this one dimension. So in total a three-dimensional integration. So delta functions that occur originally when the quantities are defined at a point, three-dimensional delta functions are in a sense then integrated over 3 dimensions and become less painful to deal with. And that's why one does it. Yeah. So this, in a sense, is similar to what, for those of you who know, in quantum chromodynamics are Wilson loops. Maybe play also a role in other fields, Wilson loops, when you discuss quark confinement. Then you also deal with A's and E's, but it's more comfortable to have the integral of A over a line, and also dealing with flux. So again, you have these analogies with Young-Mills. Okay, so now it has taken quite some time for the classical theory, but it was needed because otherwise you don't understand all these quantities. So let me, in the remaining 20 minutes, at least give you a discussion of the important methods and results of the quantum theory. So that's then part B. It's then the quantum part. And again, one can use first quantization of this here, of Ashtekaz variable, and second then the quantization of this. Loop quantum gravity refers to the quantization of that, and quantization of this, what our Ashtekar originally had in mind, is called connection representation. It was then later done for the loop case by Rovelli, Smolin and Jacobson in end of 80s and the 90s, and this has become then the more standard version. But I think it's good to know also the other, and this is because this is where it started from. So you have here the Poisson bracket, if you recall, between the A's and the E, which was 8 pi beta delta ij delta BA delta xy. And the formal quantization, as always, it's a heuristic procedure. So we put heads on it and demand that here we get commutators out of the Poisson bracket. So we get here A hat IA of x and E B J of y is then 8 pi beta. And you get an I from the quantization, and an IH bar actually, delta ij delta BA delta F. You remember we had a similar expression for the 3 metric and the momentum. So that is what you had, and you have here, okay, this IH bar. It's just the usual heuristic thing. And we go, as before, to the Schrödinger representation. That is, we implement this here as a multiplication, and this here, because it's a momentum, as a derivative. So in the Schrödinger representation, we have A operator IA of x acting on psi, which is then a functional, of course, of A only. It does not depend on the piece, as in quantum mechanics. and this is then a multiplication. Yeah, this A is a shorthand blackboard version for AIA. It has, of course, the indices and the E. Oops. Okay, the simplest constraint is, of course, the new one, the Gauss constraint, which had this form GI. You remember it was this DA, EAI. This was the classical constraint. And quantization then means this becomes an operator. It's applied on psi equals 0. And because of that here, this is very simple. So you have dA d psi over dAI equal to 0. Yeah. And this looks like the old momentum constraint, but now with reference to A. And it has a similar interpretation, which you can check at your own convenience. It just means that psi is invariant under gauge transformations of A, at least those that are connected to the identity. The old momentum constraints showed that psi does not change if you make infinitesimal coordinate transformation, as it must be, otherwise, I mean, what would it mean? And this is invariant under the gauge transformation that were written down, I mean, here, no? This here. Also, the momentum constraints, the diffeomorphism constraints, can have a similar understanding. So this A tilde equal to 0. So these are, where are they? Here, you see. Also here it's linear in E, and you can just replace this by d over dA. So also that is has a simple form, and you have FIAB d psi over d EBI is equal to 0. Of course, if you have matter fields, then there's an additional factor, but that does not cause additional problems. And what this means, if you investigate what this constraint does, is that psi is invariant under a combination of gauge transformation and infinitesimal coordinate transformation. Because originally we have here, you see, from the old momentum constraint, we have added this to get a simple form. So it's not surprising that it again describes an invariance, but this is an invariance now under a combined diffeomorphism and gauge transformation. Okay, what is with the Hamiltonian constraint? I mean, this is what most of the effort is for. Well, as I said, so in Ashtekar's original version, with beta equal I, we just have that. And then we just have here the second derivative with respect to A equals 0. And as I said before, in words, in end of 1980s and beginning of 1990s, many solutions were found. That, for example, an exact solution with the cosmological constant was found, having to do with the so-called Chern-Simons action. Also other solutions that have to do with, say, Jones polynomials and other knots, Knoten. But they are only relevant if you believe into this Euclidean version. I mean, but our world is not Euclidean. I'm afraid it's Lorentzian, and this is why it has been abandoned. So these solutions may be as nice as they are, but it's now common agreement that they are not useful for quantum gravity. But of course, mathematically they are interesting. Okay, so this was the connection representation, and what loop quantum gravity makes is is of course the quantization of this here. So this is then also called a loop representation, or loop quantum gravity for short. Now, originally in the old papers, one has started from this here and then transformed to this representation by a kind of general Fourier transform. Because that was the idea that this is maybe the starting point, the primary thing, and then you derive this. I will not write down these transformations because the modern point of view is to directly start from this. I mean, not assuming that you first have to have this underlying connection representation and then make a complicated transform where you have to prove that it exists and so on, but to directly use these variables and to directly quantize them. Nevertheless, it's good, I mean, to have seen that and to have that. Yeah, and I mean, the most complicated part of that is the choice of a basis then in that space, and this is so-called spin network basis. That I'm afraid, I mean, in the remaining time, I cannot do justice to give a very detailed introduction to this. We will also need it later. It's very important. I will give you some hints. And for those of you who are interested in the details of loop quantum gravity, please then just read maybe the book or the book by the experts on loop quantum gravity like Rovelli and others, and Ashtekar also a book. So use directly the quantized loop variables. They are called loop variables. I mean, yeah, you have the holonomy and the flux. And a complete, also normal basis for the quantum states is the so-called spin network basis. Yeah, I mean, this is important to have, I mean, a complete orthonormal basis so that you can all expand all quantum states with respect to them. Yeah? Because otherwise, if you don't have these properties, then you have a quantum state, but it's not so clear, I mean, how you do the calculations. Actually, spin networks were not defined in that context. They're much older. Roger Penrose in 1971 had introduced them for very different purpose. I mean, to discuss the discreteness of, or possible discreteness of space-time, coming from fundamental graphs attached to which are half-integer spins. So the idea that fundamentally space-time is not a continuum, but is somehow discrete, and to make it a formalism, he introduced the spin networks. And I quote from him, so from his 1971 paper, it's also in the book, the quote: "My basic idea is to try and build up both space-time and quantum mechanics," so very ambitious, simultaneously from combinatorial principles. The idea here then is to start with the concept of angular momentum, where one has a discrete spectrum, as you know, and use the rules for combining angular momenta together and see if in some sense one can construct the concept of space from this. So the concept, so that was his idea, which was an older idea, and which was then useful in that context and was elaborated on in that context. So the point is, so that goes back to Penrose, 1971, and so one has a graph called gamma n that consists of n curves. So the AI are curves. Yeah, of course they are mathematical properties. They are orientable, and piecewise analytic and so on. What you need to prove things, you make your mathematical assumptions. And also when those curves meet, they meet at their endpoints. So these are not, necessarily loops, but what you have is, for example, a gamma 4. One possible gamma 4 is then this here. Yeah. So then you have 4 curves here. And so these are called links. You could also have, for example, the following gamma 6. You could look like that. So you have here some alpha 1, alpha 2. So they meet here, yeah. And alpha 3, alpha 4, alpha 5, and alpha 6. And spin networks mean so you attach to each link now a holonomy. If you call this here the holonomy U of A and alpha. So the holonomy depends on the curve, or could also be just an open one, not just closed, and on the A, because we integrate over A. No, so associate to each link a holonomy. Then one defines so-called cylindrical functions. So one defines, this quantum states psi. They depend on the graph and on a function of A, and this is defined Fn of U1 to Un. So you have here, say, 1 to 4. So you put here a U1, a U2, a U3, a U4. And this Fn is just a general function then that maps into the complex numbers. So it's called cylindrical because it has support on this one-dimensional structure. So in a cylinder, it's like that, and you along the circle you can go in this direction. So mathematically it's called like that. And then you can define an inner product, which is similar to the standard L2 product, so integral over all these U's f star f. And you make arbitrary linear combinations, and you can show that the norm is finite and that it has nice properties. And you discuss, say, if I had 1 additional hour, I could discuss these mathematical properties and so on. There is a caveat, a disadvantage, because it turns out that this the corresponding Hilbert space, it's called so this gives rise to an Hilbert space that is also called kinematical Hilbert space, because it's for quantum states that do not necessarily obey the constraints. It's before you go to the constraint subspace, before you implement the will or the width and all that. This is kinematic, and this is well defined, but this Hilbert space is not separable. What does this mean? It has no countable basis. This basis is uncountable. You can because they can be these graphs. There are overcountably many of these graphs, right? Like the real numbers also are overcountable. It's not like the rational numbers. So this is not a separable space, which means no countable basis. This has then some partly nasty consequences. I will not explore them in quantum mechanics. Usually, as far as I know, you have separable Hilbert spaces, and other things are, of course, avoided. But here, somehow, if you like spin network, then you have to live with them. But it has disadvantages, and it's not so good for the calculations, all in all. Yeah, so you can then you can rather easily implement the Gauss constraint because this is just a gauge transformation. You make a trace over these holonomies. Like with the Wilson loops, you can construct in a gauge invariant way. The diffeomorphism constraint becomes a bit more complicated, but you can do something. Diffeomorphisms, they move these spinel quirks around, and you can identify equivalence classes. No? If you have such a spin network and the momentum constraint moves it around, so you take all of that, what you get through a diffeomorphism as a one equivalence class. The Hamiltonian constraint, I'm afraid, again, there is a huge literature, but I would say there is no final, I must say, final positive outcome in spite of many clever people having investigated. So in a certain sense, we are back to where we were also last time with geometrodynamics. And we have seen many new aspects and many promising things, but the original motivation to simplify and solve the Hamiltonian constraint so far has here also not been fulfilled. So it depends on maybe having more progress on choosing variables. But nevertheless, I want to end, if you just allow me very few minutes, end with one result that is also advertised as one important result, and this is the quantization of geometric entities. So that, okay, you cannot maybe solve all constraints, but you have this kinematical Hilbert space, and you can look for operators that you make self-adjoint in this kinematical Hilbert space and look for their spectrum. And one example is an operator that classically corresponds to a two-dimensional surface. So you make out of this two-dimensional surface, which, okay, you write it in terms of the metric, but then you have to transform to the loop variables, and you can, with mathematical rigor, you can then define an operator and calculate its spectrum, and it turns actually out to be discrete. So in a sense, in the spirit of Roger Penrose's old ideas of building the continuous space-time from discrete elements. And this is, so to speak, I think I will just use that space that is here available. So quantization of area. So as I leave this then as an appetizer for you, of course. So you quantize these two things, no? This one and this one, you turn into operators. One can then, instead of this here, have the commutational relations between, this is called U, no? U operator of A and alpha, and the E. Okay, here it's called, this is called just EI, the flux of S, which is the surface, and you find this is I times the Planck length squared. Okay, the beta, and then you have some other things that basically is the use appears here, the U quadratic. It's not so important how it looks like. Important is that you can write this down and that you can also prove that this is more or less unique, also this. And then we make this so we write down, so classical two-dimensional area, which we write in, I mean, you have then A, well, I should not use that A, I mean, another A is then the integral of a two-dimensional surface here, of, okay, to some surface element, and then we have, I mean, the square root of the two-dimensional determinant, or of the determinant of the two-dimensional metric on that surface. And this you can write in terms of, yeah, actually it's only the E, and make it a self-adjoint operator. In the kinematical Hilbert space, and this has a discrete spectrum. So for the simplest case, well, the smallest non-vanishing eigenvalue is given by the following. The smallest non-vanishing eigenvalue, and this you could call, or is called, the quantum of area, because that's the minimal area you can have. It's quantized, area is quantized, so that's the quantum of area, and that turns out to be the following. So it's a 0 is 8 pi beta times Planck length squared, and then you have this from the angular momentum algebra, and of course discreteness, as Penrose envisaged, this discreteness comes from the angular momentum algebra, because we have SU2 here. We have SO3 or SU2, and this of course gives the angular momentum algebra, which is discrete. So this is really what is behind all of that. I mean, your old quantum mechanics one results of angular momenta, but applied now to space-time. So then you have the square roots of L times L plus 1, and the fundamental, or the lowest value is reached if L is 1/2. And so this gives then, if you insert this, around 5.72 times 10 to the minus 65 centimeters squared. So at least you see one number here, one physical number, times the beta. I mean, the beta is a free parameter, but if beta is of the order of 1, then, I mean, this minimal value is of the order of the Planck length squared. Okay, the Planck length is the only dimensionful parameter here for vacuum gravity, so it must appear. So it would have to, if it's discrete, it should be related to Planck length squared. And this is the quantum called quantum of area. So the picture is, if this is correct, and I must emphasize, it's only here a result of the kinematic level, not at the level where you solve the Hamiltonian constraint, because you cannot yet solve. But at that level, if you think that this survives imposing the constraints, which I think one can assume, then it's the result that fundamentally space-time is discrete. At least concerning area, it's not so easy with volumes and lines, and so there is some discussion whether this is really true. But at least I would say it's a hint, or could show you a way in which you could look, even if it's not the final. So that's the quantum of action. Of course, this spectrum turns out not to be equidistant. Otherwise, I mean, we would have the conflict, because we don't see quantization of area here. This becomes denser and denser, so that if you go far away from the Planck length, you don't see anymore, I mean, this discreteness. Yeah, that's this very brief introduction to loop quantum gravity, but I think the main issues are there, and if you're really interested in loops, I think from this you can easily find, and in the literature on the books, ways to go on and go further. So this concludes this general formalism. So we have 2 sessions left where we really deal with the real universe. So next week with the black holes. So let us apply what we have done so far to black holes, quantization of black holes, and then in 2 weeks to cosmology, to the universe as a whole. Thank you very much, and see you next time.